Okay, next speaker is Paolo Baldan on fixed-point games and continuous lattices.
Thank you very much. So this is a joint work with Barbara, Christina, and Tommaso, who are in the audience. And the theme of the work is quite simple. We want to solve systems of equations over some fixed complete lattice. Systems are like this, where f1, fm are monotone functions. You know that a system like this has typically many solutions, and a specific one is identified by indicating for each equation via the notation eta1, eta m, whether we want the least or the largest solution. So this is the problem. And I probably don't need to convince you that this is a relevant one. Many analysis and verifications problem reduced to the solution of systems of this kind. But just to give some fix the ideas, give some intuition, let's consider two examples. First, some temporal logic over a transition system like this, where you have states like A and B, transitions between states, some atomic propositions like P, which is known to hold on B. And you want to state something like, it is always the case for any reachable state that P holds. And this you would write recursively like property X, which says P holds now, and whatever step I make, then X holds again. And semantically, this gives to a single fixed point equation over the powerset lattices of the states. And you know, or you can easily grasp that you want the largest fixed point. The least would be just the empty set. Instead, the largest fixed point is the set of states where the property holds. And dually, you can express possibility. Again, it is possible to reach a state where property P holds. You can express it recursively. Again, you get a single equation over the powerset lattice, but in this case, you want the least fixed point. And least and largest fixed point can be profitably mixed to get quite expressive languages like the new calculus. Here, you can nest least and largest fixed point arbitrarily. You can express something like, it is always the case that it is possible to reach a state where P holds. And as a system of equations, this would be a real system with two equations. One is a least and the other is the largest fixed point. And to give another example, in data flow analysis, many problems are reduced to the solution of systems of fixed point equation, which, roughly speaking, relate the information of interest at different program points. For instance, a very simple example, constant propagation. At each program point, I, you want to specify whether each variable is known to be constant, in this case, an integer, or you don't know, and then you map it to bottom. And then it's not really important how and exactly, but from a program, one derives a system of equations, and again, it is the system of equations over some lattice of information. So we want to solve this system, and very briefly, our contribution is as follows. We take several inspiration from several sources. First, from the fact that model checking for calculus is typically solved by reduction to parity games, which in turn are solved efficiently by using as an essential tool progress measures, as they have been defined by Jurdzin. Another inspiration comes from some recent lattice-theoretical characterization of progress measure, which is due to Asua and co-authors in Popple 2016. And finally, we are inspired by unfolding games on fixed point over the power set, which are kind of folklore, but you can find them in a paper by Venema. And so our contribution is the following. Given a system of equations over some complete lattice of the kind I described, with some solution, we provide a game theoretical characterization of the problem of establishing whether some element of the lattice is dominated by the ith component of the solution. And we do this in a quite general setting, that of continuous lattices. I will say a little bit more later. And we develop a notion of progress measure which works in this setting and which can be used to solve the game and so to characterize somehow constructively the solution to the problem, the solution to the system, say. And before closing this introduction, let me observe explicitly that, the problem of establishing whether some element in the lattice is dominated by some component of the solution is typically what one wants. For instance, in the mu calculus, understanding whether a singleton consisting only of a state S is dominated by the mth component of the last equation, of the solution, which means the component of the last equation, means solving the model checking problem, establishing whether the states satisfy the formula we started from. Or in constant propagation, establishing whether a function which map variable b to some constant z and all the other to bottom is dominated by the ith component of the solution means establishing whether variable b is known to be constant with value z at program point I. So, okay, this is more or less the overall picture of our results, but I have a little bit more time, so let me try to explain how the game works. Starting with a very simple sub-problem of the general one, which is a single fixed point equation over a very special lattice, which is a power set lattice of some set. So we have a single equation, a fixed point equation, which can be a largest or least fixed point equation. Eta specifies whether we want the least or the largest. And the solution is the corresponding fixed point. And we see now a game for characterizing whether some element in the set belongs to the fixed point, which is, again, a very special subproblem of establishing whether an element of the lattice is dominated by the solution. We start with the least fixed points. We want to check whether x is in the least fixed point of f. The game starts from x. It is a two-player game. The player Eve wants to show that the element is in the fixed point, and the other player, Adam, is the opponent, wants to show that this is not the case. The position of Eve, in general, an element of the set, and she wants to prove that, to support the fact that this is in the fixed point, the least fixed point. And for this, she plays some subset of S such that Y is in the image of X. And somehow, this is supporting that, very roughly, this is supporting that Y is in the fixed point because in the mind of Eve, X is a subset of the fixed point. And then Adam takes such set X and says, okay, but you say that X is a subset of the fixed point. So I pick an element there and show me that this is in the fixed point. And the game continues. It can be finite, we will see an example, or infinite. If it is finite, the winner is the last who plays. And if it is infinite, then Adam wins the game, which means that in the case of least fixed point, it is in charge of Eve proving that, providing a finite proof that the element is there. Let's see an example. We take a function over the power set of the integers, which maps each set x which transforms each set x by adding the element 0 and adding 2 to any element. The least fixed point of this is the set of even numbers. And imagine we want to prove that 4 is in the least fixed point. Then we start from 4. Eve has to play a set which contains 4 in the image, can be 0, 2. Could be even smaller, but let's say 0, 2. Then Adam pick an element there, say it picks 2. Then Eve can answer with 0, which has 2 in the image. Now Adam has only one choice. He has to choose 0. Eve can answer with the empty set, and that's it. Adam now has no moves because he has nothing to choose from. So Eve wins, and you can easily see that whatever way Adam answered, he would have lost. This is kind of a winning strategy for Eve. Instead, assuming that you want to prove that 3 is in the least fixed point, then you start from 3. Again, if you think a bit, you see that the only way to get 3 in the image is to put at least the element 1 in the set. So Eve has to play a set which contains 1, maybe something else. Then Adam can choose 1, and now Eve has no moves because he has no way of playing a set which has 1 in the image. There's never 1 in the image. The greatest fixed point game, if it were a greatest fixed point, the game would be exactly the same. But for the winning condition, finite games, again, the last player wins. But for infinite games, this time, it is if the win, and this has kind of a co-inductive flavor. And then it can be shown that for any monotone function, this game is, and for any choice of least or largest fixed point, this game is sound and complete in the sense that an element is in the fixed point if and only if as a winning strategy. So far, so good, but okay. How can we generalize this to lattices different from the powerset? What is special about the powerset lattice to make the game work? Okay, the powerset lattice is very special, but we use only very few of it. We use completeness, for sure. And then we are using this membership relation, which you can clearly represent in terms of the order relation by saying that the singleton is a subset of Y. But we actually use something more special. It's not just a generic subset, but in a sense, a small subset or a finite approximation of Y. And the sense in which this holds is the following, that whenever Y is dominated by the join of some directed set, then X is in one of the elements which are joined. And then this notion of small subset of approximation is sufficient to characterize Y, in the sense that Y is the join of all its small subset, of all its singletons. And if you look a little bit from a distance to these properties, you see, you can recognize that they are not something new to be studied. They are very well known. The first is the way below relation in lattice theory. And the second is just the requirement that any element of the lattice is the join of the elements which are way below it, which is the requirement to be a continuous lattice. So we don't need to invent anything. Continuous lattices has been invented, fortunately, by Scott in the 70s to give a semantics to the lambda calculus, and since then they've been used a lot in semantics and analysis. They include a lot of discrete structures, finite lattices, all power sets, all distributive lattices, all algebraic lattices like the one I mentioned before. And you have also continuous structure like the real interval, the set of metrics, and so on. How can we formulate the game on continuous lattices? So we have a continuous lattice. We have to fix some basis, which is a subset of elements which are sufficient to generate via joins on the rest of the lattice. And then we have a monotone function. And the game is this one. We don't need really to read because it is exactly the same as before, but for the fact that instead of checking if some element belongs to a subset in the power set, now we're checking whether if an element of the basis is dominated by the solution. And the other difference is that membership is replaced by the way below relation. And all the rest is formally the same. And you can prove also in this case a soundness and completeness result for any monotone function, for any choice of least or largest fixed point, and for any element of the basis. Okay, and somehow for this game you can also see that continuous lattices are not just one possible choice that makes things work, but somehow they're the right choice in the sense that you can prove that for a complete lattice, all games are sound, and if and only if the lattice is continuous. How can we generalize from a single to equation to a system of equations? Again, the generalization is at least formally quite simple. Now we want to show that an element of the basis is dominated by the ith component of the solution. And what changes is that in the positions of if now we specify also the equations we are interested in. And Adam, the opponent, can change during the game the position he is referring to. For the rest, essentially the game remains the same. And what changes becomes a little bit more complex is the winning condition. In the case of finite games, the winner is still who plays last. But in the case of infinite games, we have sort of parity condition in the sense that you have to take the largest index of equation which repeats infinitely often. And then if this is the index of a mu equation, then Adam is the winner. If it is the index of a new equation of a greatest fixed point equation, then Eve is the winner. Okay, so now we have a game which characterizes in a sound and complete way our problem, but we would like to solve the game. Oh, sorry. We would like to solve the game. And the technical tool which is used for solving the game is the notion of progress measure, which is, very roughly speaking, a mapping from the position of Eve to some measure of the distance of Eve from winning the game if she plays in the right way. This when Eve can win. Otherwise, the image of the progress measure from the position is just the start. It says Eve cannot win. And then one can prove that there is always a progress measure which is bounded by the F of the lattice. This can be used to show that progress measures can be characterized as least fixed points. And this provides a constructive way of solving the game. So we came to the conclusions. What we have a game theoretical approach to the solution of systems of fixed point equations over continuous lattices. We have a small theorem, a small progress measure theorem, which can be used as a tool for solving the game. I didn't present, but in the paper you can find some results about the possibility of providing a symbolic representations of the moves of the players in order to get a more efficient calculation, and an application of this to the model checking of lattice mu calculi, where the truth value of a formula is not really, it's not just a Boolean, but an element of a more general lattice. For the future, we would like to experiment with applications to other lattices, and in particularly interesting but also challenging is the case of infinite 8 lattices, where the convergence of the technique is not for free. You have to do something more clever. In particular, we are interested in studying the lattice of real intervals over the reals, for studying corresponding quantitative logics, and for reasoning about the lattice of pseudometrics. And more on the computational side, we would like to integrate in our framework up to and abstraction techniques for speeding up the calculation, even if in the case of abstraction with some approximation. And this could be well combined also with on-the-fly computation in the same way as for parity games. There are some local techniques which allow to compute only part of the solution if we are not interested in the full solution. That's it I had to say.
Okay, so we have a few questions on Slido. So have you tried to implement this?
No, actually, we're trying in the sense that there is an ongoing work, a thesis of a student, but this is not implemented at the moment. Okay.
There's also a question about the round complexity of the game for determining a winner.
Well, the point is that if you just take the plain description of the game as it is, and you compute you solve it by computing the progress measure as a fixed point without any other improvement, the complexity is going to be terrible. But for instance, what we try to do is to use our symbolic representation of the moves to end up, and we applied this technique to the model checking of mu calculus. And in that case, we get a complexity which is not far from the one which is obtained in the original work of Jurdzin. the only thing which we lose is the possibility of optimizing with respect. You get an exponential with respect to half of the okay, but okay, of the alternation depth that we do not get.
I find your title a bit misleading because you don't say anything on the solution on the equation. You answer a question about the solution, which is not at all the same. For example, in data flow analysis, you answer the question, is x equal to 2? But that's not the data flow analysis problem. The data flow analysis problem is which variable are constant and to which value. And so you need to ask infinitely many questions.
Well, that's not exact in the sense, because if you are just applying the game in a totally plain and blind way, you're right. Yes, actually, your question is very appropriate in the sense that if you do this, okay, it's not going to work. You have to check: is your variable constant 1? Is your variable constant 2? Is your variable constant 3? Which is not very. But what you can do is be a little bit more clever and ask, is my value a constant, and do some unification during the computation. Use some symbolic form of computation, and then you will get it. You don't believe so?
If you go symbolic, you change the abstract domain, you change the equations.
No, but I'm symbolic only on the value which I'm checking against. Okay, we can chat later. I don't think so.
Are there other questions from the audience? I had one question. I was curious about the theorem that you prove about characterizing the lattice. That the lattice must be continuous if all games are sound. How do you go about proving that theorem?
How the proof goes? Okay, more or less, you exhibit, in the case of a non-continuous lattice, you can find an element which is not the join of the elements which are way below it, and starting from this, you can construct a game where you can answer properly, in the sense that you are not below the least fixed point, but you answer that you are. This is more or less the proof technique. So you just take a specific element which is not obtained by the join of the elements which are way below it.
Any more questions? Okay, well, thank you.
Thank you very much.